Right now, NASA has its most detailed plan in history for building a permanent base on the moon. $20 billion, a 3-phase roadmap, a target date. For the first time, this is not a concept sketch, it is an engineering commitment. And it should terrify you, not because the plan is wrong, but because the people building it already know something that almost nobody outside the industry fully grasps. Getting to the moon was the easy part. The moon is not a destination. It is an environment. And that environment, the dust, the darkness, the radiation, the thermal swings, the silence, the isolation does not tolerate human infrastructure. It dismantles it, methodically, continuously, without pause. The real shock is not whether humans can land on the moon. We did that 50 years ago. The real shock is what happens on day 63, when the seals are failing, the solar panels are coated in glass powder, the backup power is running low, and the next supply mission is 3 months away. That is the moon nobody talks about. That is what this episode is about. This small team spent real hours verifying every fact in this video, and a like and subscribe tells the algorithm that work was worth making. In 3, 2, 1, liftoff. There is something quietly remarkable about the announcement that came out of NASA in March of 2025. After years of shifting schedules, cancelled hardware, and political reversals that had made the Artemis program feel like a promise perpetually receding into the future, the agency finally laid out in concrete, costed, unambiguous detail what a permanent human presence on the moon would actually look like. $20 billion over 7 years. A 3-phase construction roadmap stretching from the late 2020s through the early 2030s and beyond. The Gateway space station, which had been central to Artemis planning for years as an orbital waypoint between Earth and the lunar surface, was cancelled. The message was the clearest NASA had ever delivered on this subject. We are not just going back to visit. We are going to stay. The plan targets the lunar South Pole. Phase 1 runs through 2029 and focuses on robotic scouting, terrain mapping, environmental data collection, and the delivery of early infrastructure components using commercial lunar payload services. Phase 2 runs from 2029 to 2032 and introduces the first real permanent systems, pressurized habitats, transport networks, power generation, and the logistical architecture that connects them. Phase 3 begins after 2032 and aims for what NASA formally calls a semi-permanent human presence, with crews living and working on the moon not for days but for weeks, and eventually for months at a stretch. The Lunar Terrain Vehicle, which is essentially a pressurized mobile habitat capable of extending crew range across the South Pole region, is planned to arrive before the first crewed Artemis landing. Commercial lunar delivery missions are already underway, returning hardware and instruments to the surface for the first time since Apollo. This is not a vision document. It is a program with schedules, contracts, and hardware in fabrication. To understand why this announcement matters and why it demands scrutiny that goes far beyond enthusiasm, you have to understand something that almost every public discussion of the moon base skips past. You have to understand the difference between what the moon tolerates and what the moon punishes, because those are two distinct categories, and a permanent base sits entirely in the second one. For most of human spaceflight history, going to the moon meant going briefly. The Apollo program, which remains the only time in history that human beings have walked on the lunar surface, sent 12 people to the moon across 6 successful landings between 1969 and 1972. The longest any of them stayed was 74 hours, 59 minutes, and 38 seconds. That was Apollo 17 in December of 1972. Commander Gene Cernan and geologist Harrison Schmitt spent just over 3 days on the surface. 3 days that at the time represented the outer edge of what the mission architecture, the hardware, and human endurance could support. They returned to Earth, having accomplished extraordinary science and having left behind a set of observations about the lunar environment that engineers are still referencing today. The most important of those observations was about dust. Not about the vacuum, not about the temperature, not about the radiation. Cernan, during his post-flight debriefing, a formal session where astronauts described in precise operational detail what they had experienced, said something that became a kind of warning label for everyone who came after him. He said that dust was probably the greatest single inhibitor to a nominal operation on the moon. He said he thought humans could overcome the other physiological and physical and mechanical problems, but not dust. He had been on the surface for 3 days. He had no frame of reference for what 3 months would look like. Neither did anyone else. But that is exactly what the new moon base plan requires us to think about. Not 3 days, not 3 weeks, months, years, decades, if the phased architecture delivers on its promises. And the fundamental insight that almost never makes it into the public conversation about this program is that the difference between 3 days and 3 months on the moon is not a difference of scale. It is a difference of kind. It transforms every challenge from an inconvenience into a potential mission-ending failure. It transforms every degradation process from a footnote into the central operational problem. It transforms the moon from a destination that humans can visit into an environment that humans must continuously fight to survive in. Here is the conceptual shift that this episode is built around, and it is worth stating as plainly as possible before we go any further. A moon base is not a scaled-up version of a moon landing. The engineering required to keep people alive on the lunar surface for 74 hours, and the engineering required to keep people alive there for 6 months are not the same problem, with different numbers plugged in. They are categorically different problems, operating on different timescales, subject to failure modes that simply do not appear in short missions, and demanding a type of sustained operational resilience that no human being has ever actually demonstrated in a lunar environment. When you land on the moon for 3 days, you are, in an important sense, camping in an extreme environment. Your equipment is operating for the first time. Your seals are factory fresh and have never been abraded. Your solar panels are clean and at peak output. Your suit is intact and has never been subjected to repeated pressurization cycles. Your crew is well rested, recently trained, and operating on the adrenaline of something historic. The environment has had almost no time to act on your hardware, your biology, or your supply inventory. You are catching the moon in the best possible moment. The first moment before it has had any time to do what it does to everything. Now consider what happens when that same environment has been operating on your systems continuously for 4 months. The same dust that Cernan found manageable for 3 days has now worked its way into every mechanical interface in the base through 120 days of EVA cycles, airlock transitions, and surface vehicle operations. The same solar panels that were generating full-rated power on arrival are now coated in electrostatically clinging particles that have reduced their output by a fraction that may be small on any given day, but has been compounding across 4 months of continuous accumulation. The same suit seals that were pristine on first use have now been cycled dozens of times through compression, depressurization, thermal swings, and dust infiltration, and the engineers back on Earth are watching telemetry with a growing sense of unease about seal integrity on the primary pressure garment. The same life support system that was commissioned and running beautifully at the start has now replaced its first filter set, is approaching the service interval on its second, and is operating one of its backup oxygen generation units, because the primary unit flagged an anomaly on day 87 and was taken offline, pending a repair that requires a tool that was not stocked in the original spare parts. Manifest. This is not catastrophe, not yet. This is a normal day at a 4-month-old moon base, operating in an environment that the moon has been working on continuously since the moment the first habitat module touched down. And the question is not whether good engineering prevents this scenario. Good engineering is why this scenario is a normal day rather than an emergency. The question is, what happens when normal days accumulate into weeks and weeks into months, and the environment keeps pushing while the crew keeps managing, and the margin between nominal operations and genuine crisis gets narrower with each passing rotation of the moon? That is the story that NASA's new plan has made newly urgent and newly real. This is not a hypothetical future program. Hardware is being built right now. Contracts are signed. The first crewed Artemis landing is targeted for early 2028. The first permanent habitat components could follow within years of that. For the first time in human history, the question of what a permanent moon base actually requires, not in the imagination of a mission architect or the optimism of a press release, but in the hard physical reality of the lunar surface on day 90 and day 180, is not a question about the future. It is a question we are about to start answering, whether we are fully ready for the answers or not. The choice of the South Pole as the base site is worth understanding in real depth because it shapes every engineering challenge that follows. The decision was not made arbitrarily, and it was not made on the basis of scenery. The South Pole offers two things that no other part of the moon can provide simultaneously, and both of them are mission critical enough to make the site essentially non-negotiable despite its formidable difficulties. The first is what engineers call peaks of near-continuous illumination. The moon's rotational axis is tilted only 1.5 degrees relative to its orbital plane, which means the sun never rises or sets in a dramatic way at the poles, the way it does at the equator. Instead, at the South Pole, the sun perpetually skims just along the horizon, sweeping around it in a low, slow circle. At the equatorial regions, this geometry produces 2 weeks of continuous daylight, followed by 2 weeks of continuous darkness. A brutal cycle that early robotic landers have largely failed to survive. At elevated points near the South Pole, the rims and peaks of certain craters, the ridges of ancient basin walls, the combination of altitude and local topography means the sun never fully sets. These terrain features, called peaks of eternal light in some early engineering literature, receive sunlight for somewhere between 70 and 90% of each lunar year in the best locations. Some estimates push that figure higher for specific hilltops and ridge crests. For a base that depends on solar power, this is the closest thing to a stable energy source that the lunar surface offers. The second critical asset is water ice. The polar regions of the moon contain permanently shadowed regions, or PSRs, inside deep craters where sunlight has never penetrated in billions of years. The geometry of the Moon's nearly vertical rotational axis means that the floors of certain polar craters are in perpetual darkness, and their temperatures have never risen above roughly negative 230 degrees Celsius, making them among the coldest naturally occurring surface environments in the entire solar system, colder than the surface of Pluto. In these conditions, any volatile material that has ever arrived at the Moon from cometary impacts, from asteroid strikes, from outgassing of the lunar interior tends to become permanently trapped. Water ice is confirmed to exist in these regions. It was directly detected by the LC-ROSS mission in 2009, when a deliberately targeted impactor struck a permanently shadowed crater, and the plume of ejected material was analyzed spectroscopically, returning an unambiguous signal of water vapor and ice fragments. Subsequent orbital measurements from instruments aboard the Lunar Reconnaissance Orbiter and India's Chandrayaan missions have provided further confirmation of water signatures across the South Pole region. Water ice changes the entire economic calculus of a moon base. It is not just drinking water, though that matters. It is oxygen split from water by electrolysis, the same process that runs the International Space Station's oxygen generation system. It is hydrogen potentially usable as rocket fuel in future systems. It is thermal mass, radiation shielding in liquid or solid form, and a feedstock for chemical processes. If the ice can be extracted in sufficient quantities and processed reliably, a moon base can become partially self-sustaining in a way that a base with no local resources simply cannot. Every kilogram of oxygen that does not have to be launched from Earth represents a saving of roughly $60,000 at current launch costs, depending on the vehicle. A base that breathes through a supply line dependent entirely on Earth launches is an extraordinarily fragile thing. A base that can breathe its own locally produced oxygen, even partially, is a fundamentally different kind of enterprise. This is why the South Pole is the site. The sunlight and the ice, together, make it the only place on the Moon where sustained human habitation is even theoretically viable in the near term. But here is what those same features bring with them. The permanently shadowed regions where the ice is located are not next to the peaks of near-continuous illumination where solar power is available. They are in the crater floors, below those peaks, separated by terrain that is some of the most rugged, most steeply sloped, and most difficult to navigate landscape on the entire Moon. The South Pole region is heavily cratered, with enormous ancient impact basins. The South Pole Aitken Basin is the largest confirmed impact crater in the solar system, spanning nearly 2,500 kilometers in diameter, superimposed with smaller craters, ejecta blankets, and irregular topography that makes flat, stable ground for construction a premium commodity. The terrain that makes the polar environment scientifically and logistically valuable also makes it physically treacherous to operate in. Operating between the sunlit peaks and the shadowed ice deposits requires traversing this terrain in pressurized rovers, moving equipment and extracted materials across slopes and through areas where thermal gradients between adjacent sunlit and shadowed surfaces can span several hundred degrees Celsius across a distance of a few meters. Suit-clad crew members working at the boundary of a permanently shadowed crater face, a combination of extreme cold, extreme darkness, requiring artificial lighting that must be powered and maintained, and the ever-present dust that the shadowed regions accumulate over billions of years in undisturbed, utterly airless silence. The South Pole also complicates the power situation in a way that does not get enough attention in public discussions of the base plan. No single location at the South Pole receives continuous sunlight all year round. The best peaks of near-continuous illumination receive sunlight for roughly 80 to 90% of the year on average, which sounds excellent until you think about the 10 to 20% they do not. When the moon's 1.5-degree axial tilt creates its seasonal effect, the illuminated peaks at the South Pole experience what engineers call a polar winter, a period when the sun's path around the horizon dips below the local terrain features and the peak goes dark. NASA's own documentation is direct about this. The base architecture must be capable of surviving up to 8 days without solar power under expected conditions. Under worst-case conditions, the darkness can extend substantially further. Some locations experience continuous darkness, spanning the equivalent of several months during the lunar polar winter, depending on local topography. 8 days without solar power. Think about what that means for a system designed to keep people alive. Life support consumes power continuously. Oxygen generation, carbon dioxide scrubbing, water recycling, thermal regulation of the habitat interior. Communications require power. Navigation and safety systems require power. EVA preparation and suit charging require power. Cooking, lighting, and crew comfort require power. None of these can be paused for 8 days while the base waits for the sun to reappear. This is why the fission surface power project exists. Nuclear fission, not as a supplementary option, not as a backup, but as a baseline architectural requirement, is the answer to a power gap that solar simply cannot bridge at the South Pole. The fission surface power system being developed jointly by NASA and the Department of Energy targets 10 kilowatts of electrical output from a compact reactor unit. 10 kilowatts is not an enormous number. It is enough to keep critical life support and communication systems running during a solar outage, but not enough to support full operations. The base architecture, therefore, assumes a combination of solar and nuclear working together, with each providing what the other cannot during different operational phases and environmental conditions. This is the first time in the script that a specific engineering solution has been mentioned, and it immediately illustrates the defining pattern of every challenge in the Moon Base program. The solution is real, it is technically achievable, and it creates new dependencies and new failure modes that must themselves be managed. The fission reactor requires a radiator system to dump the waste heat it generates. That radiator must operate in the lunar environment, collecting dust, experiencing thermal cycling, exposed to radiation and micrometeorites. The reactor generates radiation of its own, which affects the shielding requirements of the habitat if the reactor is sited nearby, or requires power transmission infrastructure if sited far away. The fuel is radioactive material that must be launched from Earth, transported safely through the Earth-Moon transit, and handled on the surface according to nuclear safety protocols that will require crew training, specialized equipment, and careful operational planning. Every solved problem opens a new engineering obligation. That is not a criticism. That is the nature of operating in an environment that has no tolerance for incomplete solutions. The first phase of the base plan, the scouting, mapping, and data collection phase, is supposed to answer some of the most fundamental questions about whether the South Pole's advantages actually deliver what they promise. How much ice is there? In what concentrations? In what locations? And in what physical form? Can it be extracted and processed reliably using machinery that can be built and operated within current technical and economic constraints? Where exactly are the best peaks of near-continuous illumination, and what is the precise illumination profile of the candidate base sites across a full lunar year, including the worst-case polar winter? How does the regolith behave under construction equipment? Does it compact and support foundations the way pre-mission models predict, or does it behave differently in ways that affect the stability of habitat modules? These questions matter enormously because the base plan, in its current form, makes assumptions about the answers. The phased architecture assumes that ice extraction at scale is viable. It assumes that the illumination profiles of candidate sites are well enough characterized that the power architecture can be designed with confidence. It assumes that the terrain is navigable enough, that the logistics network connecting power sources, ice deposits, habitats, and landing zones can be built and operated. If any of these assumptions turn out to be wrong, not catastrophically wrong, just somewhat wrong, the implications propagate through the entire architecture. The cancellation of the Viper rover mission in 2024 was a significant blow to the Phase 1 data collection effort. Viper, the Volatiles Investigating Polar Exploration rover, was specifically designed to map the distribution and concentration of water ice at the South Pole at a resolution that no orbital instrument can achieve. It would have physically traversed the permanently shadowed regions, drilled into the regolith at multiple sites, and provided the first ground truth measurements of what the ice deposits actually look like up close. Without that data, the ice inventory of the South Pole is known at orbital resolution enough to confirm that ice is present, not enough to say with precision where the richest deposits are, how deep below the surface they extend, or how they are mixed into the regolith in ways that affect extraction engineering. The base will proceed to Phase 2 with a meaningful gap in the foundational data that the architecture depends on. This is not a fatal flaw in the program. It is a risk that mission planners are aware of and are attempting to manage through other means: commercial robotic landers, alternative scientific instruments, and the information that will be generated by the initial crewed missions themselves. But it is an illustration of the way that certainty tends to erode as you look more closely at the actual state of knowledge, supporting a plan that, in its press release form, reads as more settled than it really is. The phased plan, the $20 billion commitment, the hardware in fabrication, the commercial landers already returning to the surface, all of it is real, and all of it represents genuine progress towards something that would have seemed impossibly ambitious not long ago. But progress toward a moon base and readiness for a moon base are not the same thing. The plan knows where it wants to go. The moon, however, is not a passive backdrop against which that plan unfolds. It is an active environment that responds to every element of the plan with continuous, relentless physical force. Understanding why a moon base is so much harder than its proximity suggests means going underneath the surface of the plan, underneath the phase names and the milestone dates and the budget lines, and looking at what is actually happening on the physical surface of another world every single day that a base operates there. It means looking at the moon not as a destination that humans will someday tame, but as a set of physical processes that have been running for 4.5 billion years and have no reason to accommodate us. What those physical processes actually do to human hardware, and why the doing is so much worse than most people imagine, is where this story really begins. And it begins with something so small you cannot see it with the naked eye, something so pervasive that it reached every corner of every habitat that Apollo astronauts ever occupied within hours of first exposure, something that the most experienced lunar surface commander in history said he was not sure humans could overcome. It begins with dust, and the dust is far more than a problem. It is a permanent adversary, and the difference between knowing that and understanding it in its full engineering depth is the difference between a plan and a reckoning. To understand what lunar dust actually does to a moon base, you have to start with what it is at a physical level, because the word dust carries connotations from Earth experience that are almost entirely wrong. When most people hear dust, they think of the fine gray powder that settles on furniture, that makes you sneeze when you disturb it, that a damp cloth can wipe away in seconds. That kind of dust is the product of mechanical weathering, chemical erosion, biological decomposition, and billions of particle-to-particle collisions that gradually round every sharp edge, reducing jagged fragments to smooth, blunted grains that are relatively inert and relatively easy to manage. Lunar dust is the product of none of those processes. The moon has no atmosphere to carry wind erosion. It has no liquid water to create chemical weathering or abrasion. It has no biology. It has nothing that rounds edges or passivates surfaces. What it has is 4.5 billion years of continuous meteorite bombardment, arriving in an airless environment where every impact shatters rock into fragments with no subsequent softening process. The particles that result are sharp-edged, irregular, highly angular fragments of silicate minerals that look, under an electron microscope, like microscopic pieces of broken glass, which is essentially what they are. Some of the finest particles are glassy beads created by the heat of impact, vaporizing and re-solidifying rock material. Others are jagged crystalline fragments with acute angles sharp enough to cut. None of them have ever been subjected to the rounding processes that make terrestrial dust manageable. The particles span a wide range of sizes, from coarse grit-sized fragments down to particles smaller than 1 micrometer in diameter. The finest fraction particles, smaller than 20 micrometers, is what engineers and medical researchers refer to when they talk about the most dangerous category. These particles are small enough to be inhaled and carried deep into the respiratory system, past the nose and throat defenses that intercept larger particles, into the alveoli of the lungs where gas exchange happens. In the lungs, they behave like a chemically reactive abrasive. Because they have never been exposed to water or oxygen, their surfaces have not formed the stable oxidized layer that characterizes most terrestrial mineral particles. They are essentially raw, unpassivated mineral surfaces capable of generating free radicals when they contact biological tissue, chemically reactive molecular fragments that attack cell membranes, damage DNA, and trigger inflammatory responses. Research published in peer-reviewed journals, including Nature's partner journal, NPJ, Microgravity, has catalogued the known and potential health risks from lunar dust exposure in careful detail. Acute short-term exposure causes respiratory irritation and inflammation, as Apollo astronauts reported in real time. The chronic long-term exposure picture what happens when a crew member breathes trace amounts of dust over 6 months or a year inside a habitat that is never fully clean is, according to the scientific literature, not yet well understood. There are concerns about progressive lung damage similar to pneumoconiosis, the industrial disease caused by inhaling mineral dusts in certain mining and quarrying operations. There are concerns about neurological effects from particles that penetrate the bloodstream and reach the brain, based on studies of particulate matter in terrestrial air pollution contexts that share certain physical characteristics with lunar regolith particles. There are concerns about cardiovascular effects, about immune system disruption, and for any long-term settlement that ever contemplated permanent habitation, about reproductive and developmental effects from prolonged exposure. None of these concerns have been confirmed in human data from lunar missions, because no human has ever been on the moon long enough to accumulate the chronic exposure dose that would be required to observe them. The Apollo missions provided 12 people with a combined total of just over 11 days of surface operations. That is not a dataset that allows for any conclusions about chronic effects. The crew of a moon base will, in effect, become the first human beings ever to run that experiment. They will do so on the moon, 3.5 light seconds from the nearest medical specialist, with medical intervention capability limited to whatever fits in the base's medical bay. The dust's danger is not limited to what it does inside human bodies. What it does to hardware is equally severe and far better documented, because every Apollo mission returned hardware that showed the damage in observable, measurable form. The spacesuits that Apollo crew members wore had their primary pressure-retaining components. The joints, the wrist rings, the helmet connection, examined post-mission for wear. After just a few days of surface operations, those components showed abrasion that alarmed engineers. The joint-bearing surfaces in the suit's pressure garment showed cut marks and scoring from dust infiltration. The soft goods, the fabric layers, and rubber components showed accelerated wear. The suit's thermal control layers, designed to reflect solar radiation and maintain temperature, had their performance altered by dust that had worked into the material and changed its thermal properties. These were suits used for 3 days. A moon base requires suits that must be used repeatedly over months, cycled through EVA after EVA, each cycle abrading the seals a little more, each cycle allowing a few more dust particles to work into the joint assemblies. The new Artemis suit design incorporates improvements over the Apollo design, better materials, better sealing, improved dust exclusion features. But it is operating in the same fundamental environment against the same fundamental adversary, and the question of how it performs after 50 EVAs in the South Pole environment, the rugged, steep, shadow-edge terrain, where dust is abundant and conditions are more extreme than the flat mare terrains, Apollo used has never been empirically answered. That answer will be written by the first Artemis crews on the surface. Beyond suits, the dust attacks every mechanical system that the base depends on. Airlocks cycle every time a crew member goes on EVA and returns. Each cycle brings dust into the airlock chamber, on boots, on suit surfaces, on tools, and on equipment carried back inside. Even with brushing stations and HEPA filtration, the amount of dust that an active base generates through daily EVA operations is substantial. It settles on every interior surface. It accumulates in corners and on shelving. It infiltrates ventilation systems, coating filter media and reducing airflow. It settles on electronic equipment, creating thermal management problems, because the dust's thermal insulating properties differ from the materials it coats. Components that were designed to dissipate heat at a certain rate can run hotter when their surfaces are coated with an insulating dust layer. The mechanical destruction pathway is particularly insidious. Any interface where two surfaces move relative to each other, a hinge, a bearing, a threaded fastener, a valve seat, is a potential site for dust to accelerate wear. The irregular, angular dust particles function as an abrasive slurry inside any joint they infiltrate. Unlike a grease or a lubricant, which would tend to smooth and protect surfaces. Lunar dust in a mechanical interface acts like grinding compound, the same material that machinists use to deliberately remove material from metal surfaces during precision fitting operations. Over time, this produces wear rates that exceed design expectations, shortening component lifespans and increasing the frequency of maintenance interventions. The electrostatic behavior of lunar dust amplifies all of this. The lunar surface is continuously charged by solar ultraviolet radiation and the solar wind, and the dust particles pick up this charge. In sunlit regions, dust charges positively. In shadow, it charges negatively. At the terminator, the moving boundary between sunlit and shadowed terrain, the electrical gradient is strong enough that dust particles can levitate off the surface entirely, suspended by electrostatic repulsion from similarly charged particles below them and drawn toward nearby surfaces that carry a different charge. This levitating dust is extraordinarily fine and extraordinarily pervasive. It is drawn electrostatically to suit surfaces, to solar panels, to sensors and instruments, to anything with a charge differential relative to the local dust cloud. Solar panels are one of the most critical victims of this process. A solar panel's output is proportional to the area of photovoltaic material exposed to sunlight. A layer of dust on the panel surface reduces that exposed area and additionally scatters and absorbs incoming light before it can reach the photovoltaic material. Research and modeling suggest that unmitigated dust accumulation on a South Pole solar array could reduce output by 10 to 30% within weeks to months of deployment. On a base where power margin is already tight, where the gap between power available and power required for safe operations is carefully managed, a self-inflicted reduction of 10% in solar output is not a minor annoyance. It is a systems-level budget problem that forces the operations team to either extend nuclear power usage beyond planned parameters, reduce non-critical power loads, or implement a dust mitigation program that consumes crew time, EVA consumables, and mechanical system cycles. Active dust mitigation technologies are under development. Electrostatic dust removers that use alternating electric fields to move charged particles off of panel surfaces, mechanical brush systems, compressed gas blowers, and various coatings designed to reduce adhesion. Each of these technologies works at some level in laboratory conditions. None of them has been demonstrated to maintain reliable performance over months of continuous operation in the actual South Pole environment. Each of them has failure modes, maintenance requirements, and power costs. The story of dust mitigation on the Moon is the story of every other moon-based challenge. There are credible solutions. The solutions create new dependencies, and the new dependencies must themselves be managed continuously. The thermal environment at the South Pole deserves its own careful examination, because the common picture of lunar temperature extremes, based on the dramatic swings of the equatorial regions, does not accurately describe what the South Pole actually does to infrastructure. The equatorial regions experience the most extreme temperature range on the Moon. Sunlit surfaces at the equator can reach positive 127 degrees Celsius, and the same surfaces in full shadow cool to approximately negative 183 degrees Celsius. That is a swing of over 300 degrees Celsius that plays out over each 2-week day-night cycle, and it is responsible for the failure of several early robotic landers that were not designed to survive it. The South Pole's thermal environment is different. The sun is never high in the sky. It skims the horizon, at most, a degree or two above it, casting long shadows and providing much lower solar flux per unit area than equatorial surfaces receive. Sunlit surfaces at the South Pole may be at -50 degrees Celsius, much colder than equatorial sun-heated surfaces. The permanently shadowed regions are far colder, as previously mentioned. Some PSRs at the South Pole reach temperatures around -230 degrees Celsius. The result is not a single dramatic temperature swing, but a patchwork of temperatures across a highly varied terrain, with extreme gradients between adjacent sunlit and shadowed areas. For the base infrastructure, this means that a single habitat module can simultaneously have a sunlit wall at -50 degrees and a shadowed wall at -150 degrees, depending on its orientation and local terrain. The thermal stresses this imposes on materials are significant. All solid materials expand when heated and contract when cooled. The rate at which they do so, the coefficient of thermal expansion, is a material property that engineers account for in structural design. But different materials have different coefficients. When two different materials are bonded together, as they inevitably are in any complex engineering structure, differential thermal expansion creates mechanical stress at the bond interface. With every thermal cycle, over hundreds or thousands of thermal cycles across the operational lifetime of the base, this stress accumulates and can cause delamination, cracking, seal failure, and structural fatigue. The thermal cycling at the South Pole is not as dramatic in amplitude as at the equator, but it is continuous and it affects every material in every component of the base that is exposed to the environment. Exterior cabling, connectors, pressure vessel penetrations, structural members, and thermal blankets are all subject to this process. Materials that perform within specification for a few days may be at the edge of their operational envelope after 6 months. The qualification testing required to verify that all of these components will survive their intended operational lifetime in the South Pole environment is an enormous engineering task that is still largely incomplete for many base components. Now add the power picture to this thermal reality. At the South Pole, the base architecture must survive periods without solar power. NASA's own planning documents, including detailed thermal analysis work from the agency's engineering directorates, acknowledge a worst-case scenario of several days of continuous darkness at the base site, and that is for the best illuminated candidate locations. For other locations, or during the worst-case polar winter illumination period, the darkness can extend much further. During those periods, the entire thermal management load of the base falls on stored energy. Here is a number that makes this concrete. 1 watt of continuous heater power, sustained through a worst-case lunar polar night using battery storage, requires approximately 5 kilograms of battery mass. That number comes directly from NASA engineering analyses of surface power systems. 5 kilograms per watt of continuous heating load. A pressurized habitat module, even heavily insulated, loses heat to the environment at a rate that depends on its size, insulation quality, and the temperature differential between the interior and exterior. In the South Pole environment, maintaining habitable temperatures inside the module, while outside temperatures drop to near -200 degrees Celsius, requires substantial, continuous heater power. The life support systems, the oxygen generators, the carbon dioxide scrubbers, the water recycling systems all generate some waste heat, but they also consume electrical power, and that power budget during a solar outage comes entirely from stored energy. The fission surface power system addresses this by providing a continuous, sun-independent source of electrical power. 10 kilowatts of electrical output is the target for the initial system, enough to sustain critical operations during solar outages. though not enough to run the base at full operational capacity. For the base to function normally, solar power and nuclear power must operate together, each filling the gaps that the other cannot cover. If the solar output is reduced by dust accumulation, the nuclear system must take up more of the base load. If the nuclear system is throttled back for any reason, scheduled maintenance, anomaly response, planned inspection, the solar system must carry more of the load. The margin between these two systems working together at expected output and the minimum power required to keep people alive is the number that the operations team watches every day. Managing that margin is a full-time job. The power budget of a moon base is not a static document that gets filed at the start of the mission and periodically updated. It is a living operational constraint that changes with every change in illumination, every degraded component, every unscheduled maintenance event, and every EVA that adds to the dust loading on the solar array. The operations team on the ground, in mission control, watching telemetry from 3.5 light seconds away, makes power allocation decisions continuously. Which non-critical loads can be shed to protect the life support margin? When is the safe window to conduct a planned maintenance EVA that will temporarily reduce solar output by taking part of the array offline? How does the operations team balance the power consumed by the regolith excavators extracting ice against the power generated by the ice's eventual conversion into oxygen that reduces the demand on the base's stored oxygen supply? These are not exotic problems that require exotic solutions. They are the routine, grinding, relentless, operational calculus of running a complex system in an environment that provides no margin for error and no buffer of time between a decision and its consequences. On Earth, a power management mistake at a remote industrial facility might cause a system shutdown that inconveniences operations for a day. On the Moon, a power management mistake at a remote base might cause the oxygen generation system to fail during a period when reserves are already depleted. The stakes attached to each decision in the Moon base power budget are unlike anything in terrestrial operations, except perhaps for submarines and deep-sea habitats, and those environments, hostile as they are, have the enormous advantage of being in contact with a planet that can respond to emergencies in hours rather than months. The vacuum environment interacts with the thermal and dust picture in a way that creates a specific failure mode that most people have never heard of, but that lunar engineers regard as one of their most persistent concerns. It is called cold welding, and it happens when two clean metal surfaces in a vacuum come into contact under pressure. On Earth, every metal surface exposed to air has a thin layer of oxidized material rust, in the common case for iron, but similar passive layers for aluminum, titanium, copper, and every other engineering metal. These oxide layers act as a lubricant and a separator, preventing the underlying metal lattices from bonding directly to each other. In a vacuum, those oxide layers do not form. Clean metal surfaces brought into contact with each other, with no oxide barrier between them, can form direct metallic bonds. They literally weld together at the point of contact, even without heat, purely through the atomic scale bonding forces that are normally blocked by the oxide layer. For a moon base, this means that every threaded fastener that is installed in a vacuum environment, every valve seat that opens and closes, every hinge pin that rotates in its sleeve, every electrical connector that is plugged and unplugged is a potential site for cold welding. The consequences range from nuisance, a threaded fastener that cannot be removed without damage, to mission critical, a valve in the oxygen supply line that becomes permanently bonded in one position. Engineers address this with specialized lubricants, surface treatments, and material selections that resist cold welding. But those lubricants have finite lifespans under the combined assault of vacuum, radiation, thermal cycling, and dust. After some period of operation, a period that varies with the specific material and application, but that all materials have, the lubricant degrades, the protection it provides diminishes, and the metal surfaces begin to approach the conditions under which cold welding can occur. Micrometeorite bombardment contributes to the degradation of exposed surfaces in a way that is slow and cumulative rather than dramatic and immediate. The Moon receives a continuous rain of tiny particles, fragments of asteroids and comets that are too small to survive transit through Earth's atmosphere, but reach the lunar surface intact because the Moon has no atmosphere to burn them up. The flux of centimeter-scale objects is low enough that a person standing on the surface for a year would be unlikely to be struck. But the flux of microscopic particles, objects smaller than a fraction of a millimeter, is substantial and continuous. Over months, these impacts pit and fog optical surfaces, erode thermal coatings, and create micro-scale craters across every exposed component. The cumulative effect on a solar panel's optical coating, on a habitat viewport, on a precisely calibrated sensor, is a gradual degradation of performance that does not announce itself with a single dramatic failure, but instead creeps progressively toward the point where the component no longer meets its specification. Every component brought to the Moon has a design lifetime, an engineering estimate of how long it will perform within specification before it needs to be replaced or refurbished. In the lunar environment, the question is whether those lifetime estimates, which are typically derived from laboratory testing and modeling rather than actual lunar surface experience, will prove accurate. The first generation of Moon base hardware will answer that question empirically, one component at a time, over months and years of operation. When a component fails earlier than expected, the operations team adjusts its maintenance schedule and its spare parts inventory. When a pattern of early failures emerges, the engineering team modifies the design or the maintenance protocol. This iterative learning process is normal and expected, but it requires the base to be operating while the learning happens, which means that the first crews to live there are the ones who will discover which components fail unexpectedly and in what ways. The operations teams back on Earth are aware of this. The documentation of the lunar surface environment, the thermal analysis work, the dust impact studies, the vacuum materials testing, all of it is aimed at reducing the number of surprises the first crews will encounter. But no amount of laboratory testing and modeling fully replicates the experience of having hardware operating continuously in the actual lunar environment for months at a time. The Apollo program taught engineers things about the Moon that no amount of pre-mission analysis had predicted. The first Moon base will teach engineers things that none of the planning and testing of the 2025 to 2035 timeframe will have anticipated, because the Moon has a way of finding the gap between a model and reality and demonstrating it on operational hardware at the least convenient moment. The resupply situation is where all of these degradation processes converge into a systemic vulnerability that has no real parallel in any previous human operation. The base depends on a supply chain that spans 380,000 kilometers of space, a chain with no redundancy at the transportation link and minimum lead times measured in months rather than days. When a critical spare part runs out, when the base has used its last replacement seal for the primary airlock, when the final spare filter cartridge for the life support system's carbon dioxide scrubber has been installed, when the maintenance team has cannibalized every available donor component for a repair that was not in the original spare parts manifest, the base must wait. It must wait not for a truck delivery or an expedited air freight shipment. It must wait for the next mission from Earth, which requires launch window alignment, vehicle integration, cargo loading, and a transit that takes days at minimum, even after launch. Realistically, an unplanned resupply request could take months to fulfill from the point when the need becomes critical. Every component in the base that is subject to the degradation processes described in this section, every seal, every filter, every bearing, every optical coating, every lubricant film, is a potential node at which that resupply dependency becomes acute. Managing those dependencies simultaneously across hundreds of component types, while conducting the science and exploration activities that justify the base's existence, while maintaining crew health and morale, and while dealing with the inevitable surprises that operational experience in a new environment generates. That is the sustained operational burden that the Moon base plan has not yet fully solved, and that the Moon will not make any concessions to. The physical environment of the lunar surface, operating continuously on the base from the moment the first habitat touches down, is not a backdrop to the story of building a Moon base. It is the story. Dust, thermal cycling, vacuum, radiation, and micrometeorite bombardment are not hazards to be listed and then set aside. They are ongoing processes that shape every decision, every maintenance schedule, every spare parts manifest, every power budget, every EVA plan, and every crew rotation. They do not pause between shifts. They do not take account of how many problems the operations team is already managing. They operate on the Moon's schedule, which is the same schedule it has kept for 4.5 billion years. Understanding this physical reality in its full depth is what makes the leap from short mission thinking to permanent base thinking so jarring. Landing on the Moon is a triumph of precision engineering applied to a brief, controlled window of operations in an extreme environment. Building a Moon base is something categorically different. It is a commitment to maintain human life in that extreme environment continuously through every degradation cycle, every unexpected failure, every operational surprise, and every day that the environment has had more time to work on the hardware. Everything described in this part, the dust, the thermal regime, the power pressure, the vacuum effects, the micrometeorite rain, the resupply fragility, is the front line of the sustained operations problem. It is the visible surface of why a Moon base is far harder than its proximity suggests. But beneath this surface, working on the one element that no engineering solution can fully protect, is the set of challenges that may prove the most difficult of all. The Moon does not only attack the hardware, it attacks the people inside it, their bodies, their biology, and the physiological foundations that determine whether they can keep functioning as the environment accumulates its toll. That is where the next chapter of this story lives, in the biology of permanence, on a world that evolved to support nothing like us. Let us be precise about what we actually know regarding the human body's response to long-duration lunar surface habitation. The answer, stated plainly, is almost nothing. Not because researchers have not tried to find out, but because the data simply does not exist. 12 human beings have walked on the Moon. Their combined time on the surface totals just over 80 hours across all 6 landings. The longest single surface stay was 74 hours and 59 minutes. No human being has ever spent a week on the moon. No human being has ever spent a month there. The physiological database that mission planners must consult when designing the health protocols for a permanent moon-based crew is, at its lunar-specific core, a dataset derived from less than 4 days of maximum exposure per person, spread across a population of 12 individuals, none of whom were on the surface long enough to develop any chronic condition from the environment. This is not a gap in our knowledge. It is an abyss. The radiation picture is where this knowledge gap becomes most immediately dangerous, because radiation is the one environmental stress at the lunar surface that cannot be entirely engineered away and that accumulates damage in the human body without any immediate signal that the damage is occurring. Ionizing radiation, the kind that the moon receives in abundance from 2 distinct sources, interacts with biological tissue by breaking chemical bonds, disrupting cell function, and, in sufficient doses, killing cells outright or inducing mutations that can eventually lead to cancer. The body has repair mechanisms for many types of radiation damage, but those mechanisms are not perfectly efficient, and at high chronic exposure levels, the rate of damage can outpace the rate of repair. The 2 sources of radiation at the lunar surface operate on very different timescales and present very different challenges. Galactic cosmic rays are the baseline, the background, the unavoidable constant. They arrive from every direction in the sky, originating from violent events throughout the galaxy's stellar explosions, pulsars, the jets of active galactic nuclei, and they carry energies so high that no practical thickness of structural shielding material can stop the most energetic fraction of them. When a galactic cosmic ray particle strikes matter, whether that matter is a habitat wall, a suit material, or a human body, it produces a cascade of secondary particles through a process called nuclear spallation, generating neutrons, protons, pions, and gamma rays that can penetrate deeper into tissue than the original particle would have. The net effect is that adding more material between a person and a galactic cosmic ray source does not simply reduce the dose linearly. Up to a point, it can actually increase the dose because the secondary particle cascade from the shielding material itself adds to the radiation burden. This counterintuitive physics means that shielding against galactic cosmic rays requires not just any material in sufficient thickness, but the right material in the right geometry. Regolith is the material of choice for lunar surface radiation shielding, not because it is ideal, but because it is local and essentially unlimited in supply. Research has established that approximately 80 centimeters of lunar regolith provides meaningful protection against the secondary radiation cascade from galactic cosmic rays, reducing the dose inside a shielded habitat to a level that, while still higher than terrestrial background, is within ranges that current space medicine protocols can work with for mission durations measured in months. This is the engineering solution, and it is real. But it requires that the habitat modules be covered with 80 centimeters of excavated and emplaced regolith, a construction task that itself requires machinery, power, crew time, and multiple successful operations of systems that have never been tested at scale in the lunar environment. Before that shielding is in place during the construction phase, during early base operations, when the regolith emplacement infrastructure is still being built, the crew is operating in a partially shielded habitat on a surface where radiation levels are confirmed by direct measurement to be between 2 and 3 times higher than what astronauts experience aboard the International Space Station. That ISS comparison is worth sitting with for a moment. The station orbits above most of Earth's magnetic field, and radiation exposure is already one of the primary health concerns for long-duration ISS missions. Crew members who spend 6 months aboard the ISS return with measurable reductions in bone mineral density, measurable cardiovascular changes, and cumulative radiation doses that are tracked against career exposure limits carefully set by flight surgeons. The Moon's surface dose, without shielding, exceeds the ISS dose by a factor of 2 to 3. The first crews to arrive at a Moon base before the regolith shielding infrastructure is complete will be accumulating radiation doses at a rate that their mission architects are acutely aware of and are designing around as carefully as the hardware constraints allow. The second radiation source, solar energetic particle events, operates episodically rather than continuously, but its peak intensities are far more dangerous than the background galactic cosmic ray dose. When the Sun produces a major solar flare or coronal mass ejection, it can accelerate protons and heavier ions to high energies that arrive at the Moon within minutes to hours of the event. The largest historical solar energetic particle events, if a crew were caught outside the habitat without adequate shelter during their peak intensity, could deliver doses high enough to cause acute radiation syndrome, nausea, vomiting, immune suppression, and, in extreme cases, doses approaching lethality within hours. The Moon has no magnetic field to deflect these particles and no atmosphere to absorb them. Warning systems that detect solar energetic particle events are improving, and the typical major event provides some warning time that a crew could use to shelter inside the shielded habitat. But warning times are not guaranteed to be sufficient in all cases, and the crew's ability to respond immediately depends on where they are inside the habitat, inside a pressurized rover, or mid-EVA on a 2-kilometer traverse to an ice extraction site. A sheltering protocol for solar energetic particle events is a standard part of any serious lunar base architecture, but the protocol itself creates operational constraints. If the warning is issued while a crew member is on EVA, they must return to the habitat immediately, potentially abandoning ongoing work and creating its own set of operational consequences. If the crew needs to conduct a planned EVA during a period of elevated solar activity because a maintenance deadline requires it, the mission operations team faces a real-time risk assessment that weighs radiation exposure against mission-critical needs. These decisions are made under time pressure, with incomplete information about how the solar event will develop, by people who are separated from the crew by a 3.5-second communication delay in each direction. The partial gravity question may ultimately prove more difficult to manage than radiation, because while radiation risks are well characterized and the tools for measuring and managing them are mature, the physiological effects of 1/6 gravity on the human body over timescales of months are almost entirely unknown. The International Space Station provides the best available database for understanding how the human body changes under long-duration spaceflight, and it is an important dataset. But it is a zero-gravity dataset. The Moon's surface gravity is 1/6 of Earth's, approximately 1.6 meters per second squared, compared to Earth's 9.8. This places it in a region of the gravitational spectrum that sits between two data points we have: zero gravity and full terrestrial gravity. The assumption that the Moon's gravity is sufficient to prevent the bone and muscle deterioration seen in zero gravity is plausible but unverified. It is possible that 1/6 gravity maintains enough mechanical loading on the skeleton and muscle rigidity to substantially slow the loss of bone mineral density and muscle mass. It is also possible that 1/6 gravity is sufficient to prevent some zero-G effects while allowing others to progress. It is possible that entirely different physiological responses are engaged at 1/6 gravity that do not appear in either the ISS 0G data or the terrestrial 1G data. On the ISS, long-duration crew members lose approximately 1 to 2% of bone mineral density per month in weight-bearing regions of the skeleton during missions without aggressive countermeasures. With the current countermeasures program, 2 hours of daily exercise on specialized resistance and aerobic equipment, combined with pharmacological support in some cases, this loss is reduced but not eliminated. 6-month ISS crew members typically return to Earth with measurable bone density deficits that require months of rehabilitation to recover. The recovery process works. Most astronauts return to pre-flight health within a year, but it depends on returning to full terrestrial gravity, where the mechanical loading stimulus to the skeleton is restored. A moon base crew member who spends 6 months at 1/6 gravity does not return to full gravity at the end of their rotation. They return to a transit vehicle at something close to 0 gravity for several days, then land on Earth. Their bone and muscle status after 6 months at 1/6 gravity, followed by several days of near-zero gravity in transit, is genuinely unknown. This uncertainty extends to the cardiovascular system, to fluid distribution in the body, to the visual changes that have been documented in long-duration ISS crew members and are now recognized as a syndrome called spaceflight-associated neuroocular syndrome, involving structural changes in the optic nerve and globe of the eye that appear related to elevated intracranial pressure in the low-gravity environment. Whether 1/6 gravity creates similar fluid shifts and similar optic nerve pressure changes is not known. Whether the exercise countermeasures designed for 0 gravity are appropriately scaled for 1/6 gravity, or whether they need to be more intensive or differently structured or supplemented with equipment not currently in the base design is not known. The first crews to live at the moon base will, by definition, generate the first clinical data on these questions, and the answers will shape how the base program is managed for every crew that follows. The immune system adds another layer of biological uncertainty that has received relatively little public attention. Research conducted on ISS crew members has documented significant changes in immune function during long-duration spaceflight, including reactivation of latent viruses, herpes, family viruses in particular, that are normally kept suppressed by a healthy immune system. The stress of spaceflight, combined with altered sleep patterns, elevated radiation exposure, and the psychological pressures of isolation, appears to compromise immune surveillance in ways that terrestrial medicine does not typically observe, except in severely immunocompromised patients. On the ISS, this has been managed without serious consequences to date, partly because the ISS crew is a small, closed population with no exposure to external disease sources, and partly because the station can be resupplied with medications relatively quickly if needed. A moon base presents a longer duration of immune suppression, a more severe radiation environment, and a resupply line for medical countermeasures that is measured in months rather than days. The cumulative picture of biological stress on a moon base crew is one of simultaneous challenges operating on multiple organ systems at once. Radiation damaging DNA and potentially accelerating carcinogenesis. Partial gravity producing skeletal and muscular changes whose magnitude at 1/6 gravity is uncharacterized. Possible cardiovascular and neuroocular effects from altered fluid distribution. Immune suppression, increasing vulnerability to infection and latent virus reactivation. Chronic low-level dust exposure through habitat infiltration, producing respiratory and potentially systemic effects that medical science has not yet been able to characterize. And all of these stresses operating simultaneously, potentially interacting with each other in ways that are not predictable from studying each in isolation. Research published by NASA and in peer-reviewed space medicine literature has documented what are called combined stressor effects situations in laboratory animal studies where two environmental stresses together produce more damage than either produces alone in a non-additive way. That suggests the stressors interfere with the body's ability to repair damage from either. Radiation combined with simulated microgravity, for instance, appears in some animal studies to produce greater bone loss than either radiation or unloading alone. If similar synergistic effects operate in humans at lunar surface conditions, radiation at 2 to 3 times ISS levels, combined with a novel partial gravity environment, combined with dust exposure and psychological stress, the health management picture becomes substantially more complex than any single stressor analysis would suggest. It is important to be precise about what is confirmed and what is not. The radiation levels on the Moon are confirmed by direct measurement. The ISS bone loss data is confirmed by extensive clinical follow-up. The dust toxicity in acute exposure is confirmed by Apollo crew reports and supported by laboratory analysis of regolith samples. What is not confirmed, what cannot be confirmed without actually putting people there for extended periods, is how all of these factors interact in a real crew member living in a real lunar habitat for 6 months. The first moon base will generate that data. The hope is that the planning and the countermeasures are good enough that generating that data does not cost anyone their health. The psychological dimension of long-duration lunar habitation deserves careful treatment because it operates alongside the biological stress picture and interacts with it in ways that matter for operational performance. The crew of a permanent moon base will be living in an environment unlike any previous human habitation in several specific ways that distinguish it from the analogues that space psychologists typically reference. Antarctic winter over crews inhabit research stations in one of Earth's most isolated and extreme environments, and the psychological effects of that isolation, interpersonal tension, cognitive fatigue, sleep disruption, the phenomenon called the third quarter effect, in which morale and performance drop in the middle portion of a long, isolated deployment, are well documented and actively studied. Submarine crews live in confined, isolated environments for months with limited outside communication. International Space Station crews experience the isolation and confinement of a small habitat in an extreme environment with restricted communication. All of these provide partial models for what a moon base crew will experience. But the moon base adds dimensions that none of these analogues fully capture. The communication delay to Earth is 1¼ seconds each way, small enough that real-time conversation is possible, but large enough to be a constant, tangible reminder of the distance. Every phone call, every video conference with family, every conversation with a flight surgeon contains this tiny pause that is experientially different from any communication delay that humans evolved to manage. Over 6 months, This delay becomes part of the fabric of the crew's psychological environment, a subliminal signal that home is not just far away, but is separated by a gap that cannot be crossed in any normal human time frame. The visual environment of the moon is also unlike anything in previous human experience. The surface is a uniform gray. The sky is uniformly black. There is no weather, no cloud movement, no seasonal change in vegetation, no variety in the soundscape because there is no soundscape outside. The horizon is approximately 2.5 kilometers away, closer than the typical horizon on Earth, because the moon is a smaller body and its surface curves away more steeply. The sense of enclosed, static, featureless space that this creates is qualitatively different from Antarctic isolation, where at minimum the weather changes and the light cycles vary dramatically through the year, or from ISS isolation, where the living planet below provides constant visual variety through every orbit. The moon provides a visual environment designed by physics to be as monotonous as a natural environment can be. Space psychologists have identified confinement, monotony, interpersonal conflict, and separation from family as the primary drivers of psychological difficulty in isolated, confined environments. The moon base delivers all four simultaneously, with the additional stressor that every EVA, the primary source of variety and physical engagement with the environment, involves donning a complex pressurized suit, moving through a lethal vacuum in a sealed cocoon, and working in an environment that is actively trying to destroy your equipment. The psychological value of going outside exists alongside the physical risk and operational burden of going outside. There is no casual walk around the block. There is no sitting on a porch. There is no experience of outdoor air and sky and distance that does not require a 45-minute suit-up procedure, a formal EVA plan approved by mission control, and a constant low-level awareness that the difference between being alive and being dead is the integrity of a suit seal that has been abraded by the same dust you cannot avoid tracking everywhere you go. Managing this psychological environment requires the base to be designed with crew well-being as a genuine engineering requirement rather than an afterthought. Habitat volume, lighting spectrum, and intensity that can simulate natural day-night cycles for circadian rhythm management, private sleeping quarters with acoustic separation, video conferencing capability for personal communications with family, access to entertainment and recreational content, and planned variety in daily schedules. All of these are part of the architectural and operational design of a serious moon base. But there is a harder problem underneath the design features. The psychological health of the crew depends ultimately on the people themselves, their compatibility, their resilience, their ability to manage interpersonal conflict in close quarters, their capacity to maintain motivation and performance through the third quarter effect and beyond. And those human factors cannot be fully engineered. They can be screened for, trained for, and supported. But in the end, 6 people living together in a habitat the size of a small apartment, under the operational stress of maintaining critical systems in an extreme environment, 380,000 kilometers from home, will face interpersonal dynamics that no amount of pre-mission training can fully prepare them for. The maintenance burden, which was introduced in the previous section as a physical systems challenge, has a human dimension that is equally important. Maintenance on a moon base is not a task that a dedicated maintenance specialist handles while everyone else focuses on science and exploration. It is a collective responsibility that demands a significant fraction of every crew member's time and attention, because the number of systems requiring regular inspection, calibration, cleaning, lubrication, and component replacement exceeds what any single person can manage. The crew members of a moon base are scientists, engineers, pilots, and doctors. They are sent there to conduct research, to push the boundaries of human knowledge about the moon and about deep space operations. But a substantial portion of their productive time will be spent not on science but on keeping the base alive, replacing filters, inspecting seals, cleaning solar panels, troubleshooting anomalies, and managing the steady accumulation of maintenance tasks that the environment continuously generates. This is not a failure of planning. It is an accurate reflection of what sustained operations in the lunar environment require. The International Space Station crew members, even with a much closer and more responsive ground support team and a much shorter resupply chain, report that maintenance and housekeeping consume a larger fraction of their time than mission planners originally projected. The moon base will face this same dynamic, amplified by an environment more hostile than Earth orbit and a supply chain that is orders of magnitude less responsive. The ratio of maintenance time to science time at a moon base during its early operational years may be substantially higher than the ratio that made the program look attractive from an exploration science perspective. This creates an interesting systems tension that is rarely discussed in public moon base coverage. The scientific justification for building a moon base is real, and substantial access to the lunar geological record, the ability to conduct radio astronomy from the far side, the study of space weather and solar physics from a stable platform outside Earth's magnetosphere, the testing of deep space life support and construction technologies needed for Mars. But the scientific productivity of a moon base depends on the crew having time and cognitive resources available for science after the maintenance burden is met. If the maintenance burden is larger than projected, as it was on the ISS and as the lunar environment's unique hostility suggests, it will be the scientific return per crew member per rotation falls below what justified the program's cost. Mission architects are aware of this tension and are designing toward maximizing automation and robotics assistance for routine maintenance. But automation systems are themselves complex hardware that must be maintained, and their reliability in the lunar environment over long operational periods is not yet demonstrated. The robotics architecture planned for the moon base is genuine and important semi-autonomous robots capable of conducting surface inspections, simple repairs, and logistics operations without direct crew involvement. This allows some maintenance activities to be performed during periods when the crew is resting, during EVA windows when human presence is not required, and during solar outage events when crew activity must be minimized to conserve power. Robotics can extend the operational capability of a small crew in ways that are genuinely significant. But robotics also add to the maintenance burden. The robots themselves have sensors, actuators, power systems, and software that must be maintained. And robot systems operating in the lunar environment are subject to the same dust, thermal cycling, and radiation degradation that affects all other hardware. The most capable robot is not a replacement for a human crew member's judgment when something goes wrong in an unexpected way. It is a tool that extends the crew's reach, reduces some of their burden, and creates its own maintenance demands in the process. The medical capability of a moon base is an aspect of the human systems problem that has its own particular severity. The base must be capable of managing any medical emergency that occurs, using whatever personnel and equipment are present, without the option of emergency evacuation. A moon base crew member with acute appendicitis cannot be medevaced to a hospital. A crew member with a broken bone from a fall during EVA cannot be stabilized and transferred to emergency surgery within hours. The crew's medical officer, one member of the crew who has received enhanced medical training, but who is not a surgeon and not a specialist, must manage whatever arises using equipment that fits in the base's medical bay and medications that were loaded at the start of the mission. Ground support can provide real-time consultation through the communication link, but the delay and the limited information available through telemetry and video make remote medicine substantially less capable than physical medicine. The base medical capability must be comprehensive enough to handle the full range of medical emergencies that could occur in a working crew over a 6-month period: trauma, cardiac events, acute infections, surgical emergencies, psychological crises, with the resources of a small clinic rather than a hospital. This is a genuinely difficult planning problem. The range of potential medical situations is wide, but the weight and volume budget for medical equipment is tightly constrained. Decisions about what medical capabilities to include and which to exclude are life and death trade-offs made years before the mission launches, by people who cannot fully anticipate what medical situation will actually arise. The history of remote expedition medicine, from Antarctic stations to submarine patrols to early space missions, suggests that the emergencies that actually occur are often not the ones that planners most extensively prepared for. The moon base medical system must be designed with as much breadth as possible within its constraints, and the crew must be trained to use it, knowing that the most dangerous thing about a medical emergency at the moon base is not the emergency itself, but the absence of the support infrastructure that would make it manageable anywhere else on Earth. What this entire part of the story adds up to is a picture of human fragility in a physical environment that does not make any accommodations for biological needs. The moon has no air, no warmth, no water on its surface, no magnetic protection, no atmospheric shielding, no ecosystem to provide resources, no geological process that creates anything useful to human metabolism. Every single thing a human body needs to survive, oxygen, water, food, warmth, protection from radiation, must be either imported from Earth or extracted and processed from local resources through complex industrial operations that are themselves subject to all the failure modes described in the previous section. The human body is not a system that can wait for repairs. It has its own continuous operational requirements that cannot be deferred, that cannot be substituted, and that become more complex to meet as the biological effects of the environment accumulate over months. The moon base program is, at its core, a commitment to solve the sustained human presence problem, to demonstrate that human beings can live and work continuously on another world for periods that matter, through biological challenges that have never been encountered, with medical and logistical support that is barely adequate, in an environment that the human body evolved over millions of years in conditions that are the precise opposite of what the moon offers. That is a legitimate and genuinely important thing to attempt. The knowledge gained from doing it, about human physiology at 1/6 gravity, about chronic radiation exposure at lunar surface levels, about psychological resilience in truly isolated environments, about the interaction of all these stresses, together will be foundational for every subsequent step in human deep space exploration. It cannot be learned any other way, but learning it requires sending real people into those conditions, knowing that the answers to some of the questions will be written in their medical records, and that some of the lessons will be harder ones than the optimistic models predict. The moon will teach those lessons without mercy and without delay. The question is whether the systems and the people inside them are prepared enough to keep those lessons from becoming catastrophes. And that question connects directly to the final layer of this story, the layer that most public discussions of the moon base never reach, where the proposed solutions themselves become the terrain of the next problem, and where the true depth of what building a permanent presence on another world requires finally comes fully into view. There is a particular kind of intellectual trap that affects almost every public discussion of the moon base program, and it is worth naming directly because it shapes how people think about whether the program will succeed. The trap works like this. A challenge is identified, a solution is proposed, the solution is technically credible, and the challenge is therefore considered resolved. Radiation, regolith shielding, power during darkness, fission reactor, dust on solar panels, electrostatic mitigation, water and oxygen, ISRU from ice deposits. Each solution lands with a satisfying weight, as if a box has been checked and the program can move forward with that problem behind it. The actual engineering of a moon base does not work this way. Every solution to a lunar surface challenge is not an endpoint. It is a new system that must itself operate continuously, degrade gracefully, be maintained by a small crew under operational stress, and survive the same environment that created the problem it was designed to solve. This is the conceptual angle that distinguishes a serious reckoning with the moon base problem from a glossy architecture document, the recognition that solutions are not removals of burden, but transformations of burden, and that, in the lunar environment, the transformed burden is always significant and is never free. Consider the regolith shielding solution for radiation protection in its full operational context. The engineering principle is sound. 80 centimeters of lunar regolith placed over a habitat module reduces the secondary radiation dose from galactic cosmic rays to a level that current space medicine can work with for extended missions. That is confirmed by particle physics modeling and supported by the known shielding properties of silicate materials. The regolith is locally available in essentially unlimited quantity. This is genuinely one of the most elegant aspects of the South Pole base concept. The protection material is already there, lying on the surface all around the habitat, needing only to be moved. But moving it requires excavation machinery. Excavation machinery capable of operating in vacuum, at extreme temperatures, in terrain that slopes steeply in some critical locations, cutting through regolith that contains rocks of unpredictable size and distribution embedded in the fine powder matrix, and placing the excavated material accurately over curved habitat surfaces in thicknesses that must be consistently maintained across the entire shell. The machinery must be capable of operating continuously enough to cover the habitat before the crew accumulates an unacceptable radiation dose, which means the construction timeline matters as much as the excavation capability. If the machinery underperforms, if blade wear, motor failures, power constraints, or dust infiltration into the drive system reduces its throughput below design specifications, the shielding emplacement timeline extends, and the crew inside the habitat spends more time at the unshielded dose rate. The excavation machinery has cutting tools that must be periodically replaced because they wear against the abrasive regolith. It has actuators and bearings that must be lubricated and inspected. It has sensors that must be calibrated. It has software that must be updated and debugged. It has power connections that must be maintained. Every one of these maintenance requirements creates a window during which the machine is not operating and the shielding is not being emplaced. Every unexpected failure, a motor that seizes from cold welding of its bearing surfaces, a hydraulic line that develops a pinhole from micrometeorite damage, a software fault that causes the navigation system to misplace a load of regolith, is a delay in the shielding timeline and a corresponding extension of the crew's unshielded radiation exposure period. This is not a reason to abandon regolith shielding as a strategy. It is a reason to understand it as a sustained operational challenge rather than a one-time construction task. The shielding must be inspected periodically to ensure it has not been displaced by the settling of the habitat structure, eroded by micrometeorites, or compacted in ways that reduce its thickness in critical areas. If the habitat is expanded, if additional modules are added during Phase 2 or Phase 3 of the base plan, new shielding must be emplaced around the new modules. And the machinery required to do all of this must be maintained throughout the operational lifetime of the base. The fission surface power system, which is the solution to power continuity during solar outages, follows the identical pattern. The reactor generates 10 kilowatts of electrical power independent of the sun. That is the benefit. The operational obligations that come with it begin with the fact that a nuclear fission reactor produces radioactive waste products as a byproduct of its operation. The fuel rods that power the reactor gradually deplete, generating fission products that accumulate in the fuel and must eventually be managed. The reactor core must be shielded, not just from the external environment, but in a configuration that protects the crew from the reactor's own radiation output, which means the reactor must be sited at a safe distance from the habitats. The current architecture calls for distances of several hundred meters, and electrical power must be transmitted that distance through cabling that itself must survive the lunar environment. The waste heat from the reactor, the thermal energy that does not become electrical power and must be dumped to the environment, is rejected through radiator panels. These radiator panels must remain unobstructed and thermally coupled to the heat rejection fluid to function. Dust accumulation on the radiator surface reduces its emissivity and degrades its heat rejection capacity, which in turn forces the reactor to operate at higher internal temperatures or reduced power output. A fission reactor that cannot dump its waste heat efficiently is a reactor that must be throttled back or shut down, and a reactor that shuts down during a polar winter when the crew is depending on it, as the primary power source is an emergency by any operational definition. Maintaining the reactor over its designed operational lifetime requires inspection of components that are themselves radioactive after operation begins. Work on the reactor, whether by crew members or by remotely operated robots, must be conducted with radiation protection protocols that add complexity and time to every maintenance activity. The reactor was designed to operate for a defined period before requiring refueling or major overhaul, and that period sets a clock. When the clock expires, the base either receives replacement fuel or replacement reactor components from Earth, or it operates at reduced capacity, or it shuts down. Each of these paths involves either a successful resupply, which requires a launch opportunity and a successful landing, or an operational degradation that increases the pressure on every other power-generating system in the base. The ISRU water extraction system, which is perhaps the most strategically important capability in the entire base architecture, is also the one that carries the most unresolved uncertainty. The confirmed presence of water ice in permanently shadowed regions at the South Pole is one of the foundational assumptions of the base plan. It is confirmed at the scale of orbital detection spectroscopic and neutron spectrometer measurements from multiple spacecraft have identified hydrogen-bearing compounds consistent with water ice in the South Pole's permanently shadowed craters. The LC-Ross impact provided direct confirmation of water vapor in the plume from one specific crater. But the critical engineering question, what is the concentration of ice in the regolith? How is it distributed within the permanently shadowed regions? And can it be extracted at a sufficient rate to support base operations? Is answered with far less precision than the base architecture ideally requires. Estimates of ice concentration in lunar permanently shadowed regions range from less than 1% to perhaps 5 or 6% by mass in the most optimistic models, mixed into the regolith matrix, rather than existing as a pure ice layer. Extracting water from a matrix in which it constitutes 1 to 5% of the mass requires processing large volumes of regolith, heating it to release the water vapor, capturing the vapor before it escapes into the vacuum, and then condensing and purifying it. The energy cost of this process is significant, and the machinery required to do it at scale in a permanently shadowed crater at temperatures near -230 degrees Celsius, in complete darkness, using equipment that must operate reliably for years, is at the outer edge of current terrestrial engineering capability applied to an environment nothing on Earth fully resembles. The cancellation of the Viper rover, which was specifically designed to characterize the ice deposits at the level of detail the extraction architecture requires, means that the first crewed mission to attempt ISRU water extraction at the South Pole will be working with incomplete characterization data. The extraction system will be designed around models of ice distribution that are constrained by orbital data and by laboratory analysis of Apollo samples from other regions of the Moon, not by ground truth measurements from the specific permanently shadowed regions where the base expects to operate. If the ice concentration is lower than the optimistic end of the model range, the extraction rate will be lower than planned, the oxygen production rate will be lower than planned, and the base's dependence on Earth-supplied oxygen will be higher and will persist longer than the architecture assumed. If the ice is patchier in distribution, then orbital measurements suggest concentrated in localized deposits rather than distributed evenly through the regolith. The extraction machinery may need to be relocated multiple times, each relocation requiring significant machinery, operation, and crew or robotic time in one of the most physically demanding environments in the base's operational domain. And if the ice exists at depths below the surface that make the excavation architecture more difficult, requiring deeper drilling, more energy, more wear on cutting tools, the extraction economics shift further against the optimistic projections. None of this means ISRU will not work. It means ISRU will require adaptive management as the base learns what the actual ice resource looks like in practice versus what the models predicted. That adaptive management requires exactly the kind of operational flexibility, engineering support, and resupply capability that the Moon base architecture is trying to maintain across a supply chain of 380,000 kilometers. The solution to each problem requires the rest of the system to be functioning well. The rest of the system functioning well depends on the solutions to all the other problems being operational. The interdependence of the base's critical systems is its defining architectural characteristic, and interdependence in a hostile environment means that when one element underperforms, the performance pressure on every connected element increases. This is the systems integration challenge that sits above all the individual technical challenges and gives them their combined weight. A moon base is not a collection of subsystems that each solve their respective problems independently. It is a tightly coupled system in which the power subsystem, the life support subsystem, the ISRU subsystem, the thermal control subsystem, the habitat integrity subsystem, and the human performance subsystem all depend on each other in real time. A reduction in available power affects the ISRU extraction rate, which affects the oxygen production rate, which affects the reserve margin in the life support system, which affects how aggressively the operations team can schedule EVAs, which affects the maintenance throughput rate, which affects how quickly the dust accumulation on the solar panels can be managed, which circles back to available power. These feedback loops run in both directions, positive spirals when everything is performing well and margins are healthy, negative spirals when individual failures begin to compound. The International Space Station has experienced these negative compounding spirals multiple times in its history, and every time the outcome was recoverable because the resupply line was short and the ground support team was enormous. The most severe ISS emergencies have involved simultaneous failures of multiple interdependent systems. The ammonia leak that temporarily required crew evacuation to the Russian segment in 2013, the oxygen generation system anomalies that required emergency workarounds across multiple missions, the water recovery system failures that extended operational pressure over weeks. Each of these events was resolved, but they required rapid ground support response, expedited resupply of replacement hardware in some cases, and significant crew time and stress. The moon base will face its own versions of these compounding system stress events, with a resupply lead time that is not days but months, and a ground support team that can advise but cannot physically act. The training pipeline for moon base crew is therefore one of the most significant and least visible challenges in the program. Crew members must be trained not just in the nominal operations of every system in the base, which is itself an enormous curriculum, but in the diagnosis and repair of every system in conditions of partial information, limited tools, and time pressure. They must understand the interdependencies of the base's systems well enough to make real-time decisions about how to manage a compounding failure event in ways that prevent a manageable anomaly from becoming a mission-threatening cascade. This requires a depth of systems knowledge that goes substantially beyond the operational training that Apollo crews received, and substantially beyond the training required for ISS missions where ground teams can diagnose most problems remotely and solutions can be physically delivered in days. The training for lunar base maintenance and emergency response is being developed at NASA and its partner organizations. Analog environments, underwater habitats, Antarctic research stations, isolated test facilities are used to simulate some aspects of the operational challenge. High-fidelity simulators provide exposure to base system failures in controlled environments where mistakes do not kill anyone. But no training environment fully replicates the combination of isolation, physical stress, equipment degradation, partial information, and time pressure that a real base emergency presents. The gap between training and reality is a permanent feature of operations in genuinely novel environments. What preparation does is reduce that gap and give crews tools to manage the things that the gap reveals. Autonomy and artificial intelligence represent a genuine and growing contribution to the moon base architecture that deserves honest assessment. The base plan incorporates progressively increasing levels of autonomous operation systems that can detect anomalies, diagnose their likely causes, and in some cases, initiate corrective responses without immediate crew involvement or ground team authorization. This is important for several reasons. The communication delay, while small by interplanetary standards, is still long enough to matter in a rapidly evolving emergency. A system that can detect a seal pressure anomaly, close the affected section, and alert the crew simultaneously, rather than waiting for telemetry to reach Earth, be analyzed by a ground team, and a recommendation be transmitted back, is a system that provides a meaningful operational safety margin. Autonomous monitoring and response for non-emergency anomalies reduces the cognitive load on the crew by managing the routine inspection and alerting tasks that would otherwise require continuous human attention across hundreds of sensor channels. But autonomous systems introduce their own failure modes. A system that is programmed to close a valve in response to a certain sensor reading will close that valve even if the sensor reading is the result of a faulty sensor rather than an actual anomaly. A false positive in an autonomous safety response can create the same operational disruption as the real event the system was designed to prevent. Artificial intelligence systems that learn and adapt to the base's operational environment can develop behaviors that were not anticipated in their design, especially in novel situations that fall outside their training distribution. Managing the interaction between autonomous systems and human operators, knowing when to trust an automated decision and when to override it. How to maintain situational awareness across a base where autonomous systems are making hundreds of small decisions continuously is itself a human factors challenge that adds to the cognitive complexity of living and working in the base. The question of what role Earth-based ground support plays as the base matures is one that the program has not yet fully resolved. Early base operations will likely be heavily dependent on a large, active ground team similar in scope to ISS mission support, but adapted to the different communication dynamics of lunar operations. Over time, as the base becomes more autonomous and as the crew's operational expertise grows, the expectation is that the ground team role will evolve towards something more advisory and less directive. But this evolution requires carefully managed transition points, and the autonomy of the base from Earth-based support cannot develop faster than the crew's capacity and the automation system's reliability justify. The cost of the program, $20 billion over 7 years for the base construction phase, with operational costs presumably continuing indefinitely. Beyond that is a number that must ultimately be justified to the political systems that fund it. This is not an engineering challenge, but it is a real constraint, because the base's ability to sustain operations over the decades required to generate its full scientific and operational return depends on sustained political and budgetary support from governments and their tax-paying populations. The history of space programs includes examples of ambitious plans that were curtailed by political and economic forces that had nothing to do with their technical viability. A moon base is not immune to this. It requires not only that the engineering work, but that the public case for it remain compelling across multiple political cycles and funding cycles, many of which will occur while the base is in difficult, unglamorous, operational phases rather than at the dramatic moments of first landings and first habitations that generate public enthusiasm. The scientific return of the base and its value as a stepping stone toward deeper human exploration is genuine and should not be undersold. Sustained access to the lunar surface enables geological sampling at a scale and continuity that robotic missions cannot match, because humans can make contextual judgments about which samples are scientifically significant that no current robotic system can replicate. A permanently staffed observatory on the lunar far side, shielded from Earth's radio frequency interference by the entire body of the moon, would provide radio astronomy capabilities that cannot be duplicated from Earth or from Earth orbit. The base's construction and operations will generate the engineering data required to design the Mars architecture that follows, because Mars will present many of the same challenges the moon presents: radiation, partial gravity, dust, isolation, supply chain fragility, but amplified by a distance that makes the moon look like a commute. Everything learned about sustained operations on the moon directly informs the feasibility of human Mars exploration. This is not a rationalization for the moon base. It is a genuine strategic argument for it. But the genuine strategic argument does not dissolve the genuine operational difficulty. The moon base will be hard. It will be harder than the planning documents suggest. It will reveal failure modes that the models did not predict and generate biological data that the medical community did not anticipate. It will require the people inside it to sustain performance and resilience under conditions that have no direct precedent in human experience. It will cost more in resources and in human health than the optimistic scenarios project, and it will be worth it, not because building hard things justifies the cost automatically, but because the specific things this particular hard thing will teach humanity about living beyond Earth cannot be learned any other way. The deepest truth of the moon base is not a technical truth. It is a truth about the nature of permanence in a hostile environment. And it is this: the moon does not become less hostile when humans decide to stay. It does not accommodate the decision. It does not acknowledge the engineering effort that went into preparing for it. It does not recognize the courage of the people living inside the habitats, or the brilliance of the teams that designed them. It simply continues operating as the physical environment it has always been, cycling between darkness and cold, and radiation and dust and vacuum and micrometeorite, rain, applying the same physical processes it has applied for 4.5 billion years to every surface and every system and every biological body that commits to being present in it. What a moon base requires, understood fully, is not a set of solutions to a set of problems. It is a permanent institutional commitment to operating in an environment that will generate new problems continuously at a pace that reflects the moon's indifference to human timelines. The base will need to be maintained longer than the careers of the engineers who designed it. The biological and operational data it generates will be studied by scientists who have not yet been born. The failure modes it reveals will be incorporated into the design of systems that have not yet been conceived. Building it is not the culmination of a program. It is the beginning of a relationship with another world, a relationship defined by the moon's terms, not ours. The $20 billion plan exists. The hardware is being built. The first landing approaches. But between landing and staying, between visiting and belonging, there is a gap that no budget line captures and no press release acknowledges. It is the gap between what the moon permits and what human permanence demands. It is filled not by a single engineering achievement or a single moment of courage, but by 10,000 separate acts of maintenance, by years of quiet physiological adaptation, by operational decisions made in the middle of the night when a sensor reading does not look right and the next supply mission is 4 months away. The moon is close enough to see with the naked eye on any clear night. It is close enough that its craters have been named by people who never expected to walk among them, and then by people who did. It is so close that humans crossed the distance with 1960s technology and returned safely. That proximity has always made it feel manageable, almost within reach, almost ordinary in its accessibility relative to the rest of the cosmos. And that feeling, the feeling that the moon is merely demanding rather than categorically hostile, is the most dangerous misunderstanding in the history of human space exploration. The moon is not waiting to be settled. It is not waiting for anything. It is doing what it has always done, grinding surfaces to powder and cycling through darkness and cold with a patience that makes all human timescales irrelevant. The question before the engineers and the astronauts and the mission planners of the coming decade is not whether a moon base can be built. The hardware exists. The knowledge exists. The plan exists. The question is whether everything built can be kept running, whether permanence, in an environment engineered by physics to resist it, is something that human intelligence and human stubbornness can actually sustain. We have never answered that question before, not once, not on any world other than the one we were born on. The moon base will be the first attempt to answer it, and the moon, as it always has, will mark every answer honestly. Sleep well. Stargazer, the grey world above you keeps its silence, and the work of belonging to it has only just begun.